Okay, this is a cartoon just showing how one of these things forms. If we have a star on the main sequence, so a star on the main sequence is a normal star, like our sun, which is burning fuel and which is stable. It runs out of fuel, it becomes something called a red giant. Have people seen Betelgeuse in the night sky? Okay, so Betelgeuse is probably the most famous red giant star. So it expands into this red giant phase. And when it reaches the end of that phase, then it collapses in on itself, it forms a neutron star, the outer layers go off to form the supernova. Let's just take a little overview of pulsar properties. And again, these things are just really, really exotic objects. And I like doing these public lectures because often when you do this research every day, you kind of forget how really interesting and amazing these types of things are. So if we took a teaspoonful of neutron star matter, if we could go to a pulsar and stick a teaspoon in, and we took a teaspoonful of matter, it would weigh as much as an ocean-going supertanker. It's the largest supertanker on Earth, just one teaspoonful of this neutron star matter. So it's incredibly dense. And one of these objects can rotate faster than your kitchen blender, okay? Up to 700 hertz. The fastest pulsar has a spin period of about 1.4 milliseconds, okay? So very, very fast rotation. They have super high magnetic fields. And these magnetic fields are what really drives all the very, very interesting physics that we see in these objects. They also have really high space velocities. If we look at how fast these pulsars are moving through space, they can be moving at velocities of 1,000 kilometers a second. Okay? So that's a heck of a lot faster than, of course, anything can move on Earth. It's a heck of a lot faster than even normal stars move. Okay? Can you think of why they might be moving so fast? There was this massive explosion, and it gives them a big kick, and so that sends them hurtling off through the galaxy, through space. Okay, so these are really interesting things to study. So why do they spin so darn fast, right? How do we take a star and make it spin up to 1,000 times a second? Any ideas? So what happens if you are ice skating and you're going in a circle and then you pull your arms in? You speed up, right? Okay. So that's what happens with pulsars too. We have a star like our sun, which is rotating about once every month or so, okay? And then we make it a heck of a lot smaller, and so it speeds up and goes a whole lot faster. And so that's what happens with pulsars. This is conservation of angular momentum. Okay? And these collapsing cores can spin up to something like a few millisecond periods. Okay? This also amplifies the magnetic fields. This is why they have such high magnetic fields as well. Our sun has a magnetic field. And when the star collapses, the magnetic field is amplified as well. Okay, so this is obviously not a real pulsar. This is a cartoon of what a pulsar might look like if we could see it. Of course, they're much too small for us to actually be able to image the surface of a pulsar. So here's the neutron star. And pulsars are not actually pulsing. It's a common misconception that we have a star and it's actually kind of heaving in and out and pulsing. It's not doing that. What we see as pulsations is actually a lighthouse beam of radio emission. Okay, so the pulsar has a north and south magnetic pole, and it turns out these pulsars have magnetospheres of ions and particles that get accelerated along the north and south magnetic poles and radiate. Okay, so we're seeing emission in this sort of lighthouse beam. Because the pulsar is rotating, every time this beam passes our line of sight, we see a little blip. We see a little radio pulse. And this is what we might see with our radio telescope along this bottom panel here. Okay, so one really fun thing we can do is we can go to a telescope like the Green Bank telescope, and we can point at a particular pulsar, and we can digitize the signal. We can actually listen to the sound of a radio pulsar. Unlike what Jodie Foster would have you believe, this is not how we actually do astronomy. We don't actually sit at telescopes and listen for new things, but we can do this. So let's just listen to what a couple of these pulsars might sound like. I hope this works. This is a pulsar which is spinning a little bit faster than once a second. Okay. Pulsars have a wide range of spin periods, though. Whoops, let me go back. So this one here is actually the Crab pulsar, this very young pulsar in the supernova remnant. Okay. It's not very pleasant, so I'll stop. Here is another quite young pulsar. This one sounds kind of like a horse galloping. And then I have two other pulsar sounds. And these pulsars are millisecond pulsars, which are a special type of pulsar that spins really, really fast. And when we hear that they spin so fast, we actually can hear each pulse. They're just going to sound like a continuous tone. OK, so here's 1 millisecond pulsar with a period of about 6 milliseconds. OK, not very nice. And here is, it used to be the very fastest pulsar known, but now we know of one that's spinning a little bit faster. Here's the second fastest spinning pulsar known. OK. So hopefully I've convinced you that these objects are pretty interesting and pretty exotic. It's this precise periodicity which makes them very interesting to study. Okay? They really are like little cosmic clocks. We can time them very precisely, and we can study a whole range of physical scenarios that these pulsars end up in. Okay, so where do pulsars live? Where are they located in the galaxy? They pop up all over the place in the galaxy. Okay, currently we know of almost 2,000 of these pulsars. All of them are in our own galaxy. They're quite faint, and we haven't detected any pulsars yet in other galaxies, although we might find some very soon. Tabitha and I, one of my students, were looking at M31 to try to detect some very distant pulsars. Right now, though, we don't know of any in other galaxies. They're in all sorts of different scenarios. Lots of these pulsars have binary companions, so they're in binary orbits with other stars. We see some of them in these clusters of stars called globular clusters. We see some of them, of course, in supernova remnants, because that's where they're born. Incidentally, we only see about 20 of these 2,000 are actually still in the remnants. This is because they move so fast, they escape the remnants pretty quickly, and also the remnants fade very quickly as well. We see a couple in the large and small Magellanic Clouds, which are very small satellite galaxies to our own, but we don't really call them extragalactic pulsars. So let's look at pulsar properties in a little bit more detail. Okay, so we can see the radio emission from these objects. One really fundamental thing that we'd like to get at about any new star, any new object we discover is how far away is this thing, right? Who's used a prism? I'm sure people have seen prisms before, right? Okay, so if we take light and we shine it through a prism, we'll see that the different wavelengths of light are spread out due to refraction, right? There's a kind of similar effect that happens with radio signals in the interstellar medium. So the interstellar medium is the stuff in between us and a star. There's lots of free electrons in the interstellar medium. And what these free electrons do is they disperse a signal. So if a signal comes out and it's emitted over a wide range of frequencies, the high frequency part of the signal gets less dispersed and the low frequency part gets more dispersed. So this is a pulse from a pulsar, and if this is frequency, so we split our radio bandpass into a bunch of little frequency channels, we see that the high frequency bits show up here and the low frequency pulses are delayed. Okay? So for pulsars that are far away, we probably expect to see more of this delay, and for pulsars that are nearby, we expect to see less of this delay, because pulsars that are farther away have more stuff in between us and them, and their signal needs to travel through more of this dispersing stuff. So this is how we get a handle on pulsar distances. Okay? It's not perfect, because we need to make a model for this stuff in between us and the pulsar, but it's a good way. And here's a plot of all the pulsars projected down onto the plane of our galaxy. So if we could go above our galaxy and look down, here's the center of the galaxy, and here's the sun. It's a little yellow dot right there. You can see that most of the pulsars, these black and yellow points, are centered around the sun. Okay? Do we really think that by chance most pulsars just happen to be centered right around the sun? Probably not, right? This is just because it's very difficult to detect them in the galactic center, because they're A, more distant, and B, there's lots of stuff in between us and the galactic center that interferes with the signals.